Artisan. I'm Simon Danucci, and I've been a safety engineer and consultant for over 20 years now. So when I decided to start my own business, I was wondering what I was going to call it. And I looked around at various names, some of which were already taken, and I came up with the name The Safety Artisan for the business and the website safetyartisan.com if you want to take a look. And I came up with that name because I liked the word artisan and what it meant and the connotations. So first of all, I mean, artisan means a skilled person who does something by hand. And it can also refer to a thing that is, specially handmade, usually with high quality materials. So I like the sound of that. And I think it's appropriate, even in this modern age where I've worked on, huge projects, multi-billion-dollar projects that lasted for years and involved thousands of people. Because even on a big project, we're still relying on individuals being competent to do a job and to know how to do it, and to have that skill and that awareness and that understanding. So that artisanship, that appealed to me. I thought that's good. And another thing was that there's this connotation of somebody working alone at home, maybe a sort of a cottage industry type setup that used to exist before the Industrial Revolution. Or I should say, before the first Industrial Revolution. Now, whichever Industrial Revolution we're currently in at the moment, I don't know. But we've gone back to a world where, thanks to the internet, you can sit at home and do work. And in fact, thanks to, the recent global pandemic, more and more of us have been sat at home doing work, working remotely over the internet. And I, as an individual, can reach hundreds, thousands, or even millions of people over the internet with my teaching and with my knowledge and experience. So, the internet has really enabled a return to those kind of cottage industry ideals where individual people can do something of high quality and find a market for what they're doing, regardless of, big brand, big business, etc., etc. So we can, you and I can communicate one-to-one or one-to-many, and you can communicate with me, and we can learn together and share together what we want to do. Now, if that sounds good to you, if that sounds something that you're interested in, then please check out the videos and other learning products at safetyartisan.com. And you'll also find me, Simon Danucci, on udemy.com. So if you want to see what I do on a third-party platform, and then that's there too. Okay, well, thanks very much. And I look forward to seeing you again soon. Cheers. No. That's quite enough from him. Anyway, good morning, everyone, and welcome to the webinar. I'm Simon, and today, as I've said before in the run-up to this, I'm going to be talking about system safety within a systems engineering framework. So before I go any further, can I just check, can you hear me? If you can hear me, can you give me a hold on, I've got a weird message, never seen that before. Anyway, not to worry. Can you let me know if you can hear me okay? I'll just send a message. So, just before we get going, I'll just check that we should be working okay. And yeah, I'm getting mic output here. Thank you, Rebecca. That's great. Thank you very much. Right. So this morning we've got the 5th in a series of 5. So this is the last one for the moment on my series going through Mil-Std-882E, system safety standard. And what we're going to do is this morning I've got some slides for you, and then we've got an open question and answer session. So if you've got anything you want to ask me about system safety, not just on what I'm presenting, but anything at all, then do please be thinking of some questions, and we'll chat. Okay, so I'm just going to share my screen with you. Okay, now you can see me looking at me, but let's go to the PowerPoint. So what we're going to talk about, as I've said, is hazard analysis within systems engineering. And we're going to be looking at 3 tasks in the MIL standard. And as it says, it's a free webinar from the Safety Artisan. So, and talking of free, there's quite a few free resources I've put in the chat with links. So do check them out. So a little bit about myself first. I've got about 25 years experience with system safety in various industries, mostly defense. And I've worked on a lot of different kinds of aircraft. I've worked on ships and submarines, air traffic management systems, trains, a little bit on trains and automobiles, software, and yeah, lots of electronic comms and EW systems, all kinds of stuff. And I've been privileged to work on some quite small programs, which is great because you get to do everything yourself, right through to some enormous programs. And Eurofighter and Future Submarine are 2, both of them multi-billion-dollar programs, tens and tens of billions. Future Submarine failed, sadly. So it wasn't all good times, but you get the benefit of learning from the mistakes that I've seen and the mistakes that I've made. None of us are perfect. You look back on things and think, no, I wish I'd done things a bit differently. But you can reap the benefit of that. And as you might be able to tell from my accent, I'm from the UK. So I had a career in the UK. Then I moved to Australia, and I've been here just over 10 years now. And I've worked on a lot of US and European programs. So I've seen a lot of different ways of doing things. We all do things slightly differently, which is fine. It's been very interesting to see how different countries do systems engineering and safety engineering. And then on the teaching front, I was part of the team at Kinetic in the UK. We had the contract to teach system safety to Ministry of Defence staff, and so we taught hundreds of people over I was there for sort of on it for about 5 years. We taught safety to hundreds of people, and I also authored some bespoke courses for particular teams in the MOD. And then I've also taught thousands of people online. So and been privileged again to present safety topics at a number of international conferences over the years. Well, software and safety, I should say, because it hasn't always been safety. I started in software before then.
So anyway, that's me. So that's, that's maybe why I've got something worth saying. Let's hope so anyway. So, and today we're going to be talking about hazard analysis in systems engineering. How do we, posh word is integrate, a fancy word. How do we fit it in? How do we fit it together? How do we, get it to work? That's what it's really all about. So that's what I'm going to talk about. Now, I've said we're going to talk about these 3 tasks. So in the 200 series tasks in the Mill standard, they are all the analysis tasks. So, and it starts with 201 and goes all the way through to 210. But today we're going to talk about 3 tasks in overview, very briefly, because each one is quite a big topic in its own right. So we're going to talk about task 204, subsystem hazard analysis, task 205, system hazard analysis, and task 209, system of systems hazard analysis. And I will explain what those terms mean, subsystem, system, system of systems, in practical terms. Okay, I'm not going to give you a dictionary definition, but we'll talk about stuff as it pertains in the real world, which hopefully you will find more useful. Okay, so you've noticed I was going to add some text on the left of that slide, but I didn't get around to it. Never mind. So what we have here, as I'm sure you're aware, is the classic V model that we refer to often in systems engineering. And so really the V model is just a straight through waterfall model, but it's been bent. And the reason for that is that we make the point that as we go down the left-hand side of the V into more detail, we're also creating the tests and verification methods, etc., that we're going to need on the other side of the V. So right from the beginning, we are thinking about, okay, I've got this concept for something I want to do. I'm turning it into requirements and architecture, and from there into a design and implementing the design. At every stage, when I'm putting this all back together, when I'm integrating it, when I'm testing it, when I'm verifying it, when the customer is validating it, and when it gets released or certified to go into service, how are we going to do that right-hand side of the V? Okay, so the key point here is we're thinking about the end game right at the beginning at every level. Okay, and by doing that explicitly right from the beginning, we build a better product because we build a testable product. We can build a product where we can assure ourselves that it's going to work, it's going to do what it's supposed to do, and not do things that it shouldn't do. Okay, and that's more where the safety comes in. So one of the properties that we're going to demonstrate as we go through the systems engineering life cycle is we're going to demonstrate that the thing, whatever it is going to be safe. Okay, and if we think about that right from the very beginning, and at the beginning we think about what's the end game, where are we going to, that makes it much more likely that our project is going to be successful. Okay, so that in a few words is systems engineering. Now obviously there's a lot more to it than that. If you went on a proper systems engineering course, it would take a week, and then you'd need lots of experience and study, but that is basically it. Or I should say, it's enough for our purposes today. So I promised you that we would talk about systems and subsystems. So here we have a little illustration. So right in the middle here, we have our system of interest, the system that we're developing. And that system is broken down here into a number of subsystems. And we've gone down 2 layers. There might be fewer or more, it doesn't really matter. But the point is that we are making or buying these subsystems, and we're getting components for them. And then we are integrating. We're integrating each subsystem, because typically a subsystem has a particular a number of requirements allocated to it. It's got to do certain things. So we might test the subsystem, and then we're going to put it together into the system and test it all together. Okay. So, and as I say, some we might be developing in-house, others we might be getting from a subcontractor, or we just might be buying stuff off the shelf if we can. Okay. So that's how we put together our system. And in systems engineering, we hopefully will have a specification for our system that we have developed from the customer requirements. And then probably if we're going, well, whether we're going out to purchase or going to a subcontractor to develop, we're going to have some kind of specification for each subsystem saying this is what the subsystem needs to do in order to contribute to a successful whole. Okay, so we need each subsystem to do certain things and have certain properties and attributes and all the rest of it in order to have a successful system. And of course, to do that, we must have worked out what those properties and functions for each subsystem must be. And again, safety gets to play its part in doing that. More on that later. So we have our system. Maybe it interfaces with other systems, and our system and these other systems live in the real world. They work in the real world, so they've got to interface with their environment. And also the tools at the top. Very often we have a support system that well, supports the operational or mission system and keeps it going and keeps it up to date, keeps it running, keeps it working. So we've got all of these things we're working with our mission system that it has to work with to one degree or another. And if we want to think about the safety of how our system and those other systems interact, that's what we might call a system of systems analysis. Okay, so we will analyze at the systems level, at the subsystem level, and perhaps at the system of systems level. Excuse me. I'm a bit croaky this morning. It's too early. Okay, so first of all, let's talk about subsystem hazard analysis. And I'm doing these tasks in the number order. This isn't necessarily the order that you would do them in. So, as it says, there are 3 big parts to task 204. So we're going to perform and document the analysis. So we're going to do that to verify subsystem compliance with requirements. Okay, so part of the task is we've got these requirements on the subsystem that relate to safety. Does it actually comply? And those requirements are to, as it says, to eliminate hazards, or if we can't do that, to reduce the risks. And also in this analysis, when we're thinking about our subsystem, we might identify new hazards that hadn't been spotted before, because we're going to go down to a level of granularity and maybe discover some stuff about the implementation or components or whatever, and go, okay, we're going to have to do things in this particular way, which makes these hazards arise. And of course, we're not doing analysis for its own sake. As we design subsystems, for the safety analysis is going to help us recommend actions to take to eliminate hazards and to mitigate their risks. So we're doing this, we're not doing analysis for analysis' sake, we're doing it to ultimately to identify controls that will control the hazard to an acceptable degree, an acceptable level, whatever that might be. So that is basically task 204. When we get to 205, you'll see it's very, very similar. Just a slightly different language. Now, I've just got a couple of slides of comments on 204. One of the comments in the standard, it gives some hints about areas to consider. So we should be thinking about performance and the degradation of performance. We should be thinking about functional failures. And as it says, timing, design errors, defects, inadvertent functioning. Okay, which to me, inadvertent functioning is all part of functional failure. But so there are some techniques that we might use. We might use, again, my favorite, functional failure analysis, or a FMEA, a failure modes effects analysis, or a FMECA, where we put criticality in the FMEA as well. But with an FFA, we might be looking at, no function, inadvertent function. So it doesn't work, it works when it shouldn't, or it works, but it works incorrectly. Okay, and really a lot of the difference between the different analysis techniques is how deep do we go. So FFA just asks those three questions. In a FMEA, we would drill down and we would look at each failure mode, because there could be multiple failure modes for each one of those, particularly incorrect function. There'll be lots of ways something can go wrong. As it says, timing errors, too early, too late, too slow, too fast, whatever. So you could do a FMEA or you could do a HAZOP to look at things like that. And you could drill down to each failure mode, each sort of component failure, if you need to go that deep, of course, because the deeper you go, the more expensive and time consuming it gets. But that's the kind of thing that we might be doing to look at the performance of a subsystem. And these techniques are good for identifying hazards, but not just for identifying hazards. They will also show up performance issues, non-compliances, things that could go wrong. You think, okay, well, that's not desirable. What might we do about either preventing that failure mode or managing it, or warning the user, maybe, whatever it might be. So that's of interest there. Now, I mentioned warning the user. While we're doing all of this, we've got to think about human beings, human operators and maintainers. I come from a maintenance background, so don't forget the maintainers. And we've got to include the human in the loop, okay? So the human operator, maintainer, they're going to observe things, they're going to receive information, and they're going to maybe issue commands or direct what's going to go on. So there's various techniques that we can use to include the human in the loop. I've mentioned HAZOP, hazard and operability analysis. So we could consider information flow to and from the human operator. So that might be a control HAZOP or a computer HAZOP, a CHAZOP, which is a specialization. And there are lots of specialist human factors analysis techniques. And we might use some different conceptual models to help us think about all the different human factors. Now, 5M and Shell are old models in the Federal Aviation Authority System Safety Handbook. There's lots more modern models that are out there and modern techniques. If you want to know more about human factors, I had a chat with a friend of mine who is a brilliant human factor specialist, and I've worked with him. I know how good he is, called Peter Bender. And so if you want to see my chat with Peter, where he explains a lot of good stuff about human factors, the link is there. It's also in the chat. Okay, I put that link in the chat. So you can go on YouTube and see and hear that conversation with Peter, where he talks about human factors. I'm not going to say any more now because, it's a whole hour we spent just talking about the very basics. So let's move on. So third, and I think final slide on 204, we need to do some compliance checking. So hopefully we have a subsystem specification, or maybe if we bought something off the shelf, maybe we've also bought the user manual and the maintenance manual, and we can check through in there. or there's a specification that comes with the product. And we may also have derived some safety controls, some hazard controls that we need from our hazard analysis. So we think, okay, I've now got these derived safety requirements, these DSRs, these controls, got to make sure that verify that they are in and they work. And a lot of this is going to be assessing documentation. So as I said, it might be salesy stuff, it might be manuals. Hopefully the manuals contain warnings and cautions of, you know, the dangers of the system, or the subsystem, sorry. Or maybe they're in a separate booklet. Maybe we've got a training needs analysis and training materials. And of course we can physically or virtually inspect the system. These days, maybe we can do a video walkthrough, you know, or we can look at computer design, CAD CAM, or a virtual walkthrough. There's all kinds of ways we can look at the system or its representations in, you know, in documentation or digitally. So there's lots of things that there's lots of ways to do compliance checking of a subsystem. So there's some, I hope, useful hints about how to go about this process, what you need to do and how you might do it. Okay, let's move on to system hazard analysis, which is task 205. So 205 is very, very similar to 204. There are some slight changes in the wording. And in fact, when I do the full lessons on 204 and 205, I actually spend a lot of time talking about only the differences, because the two tasks are very, very similar. But again, we've got to verify system compliance. We've got to identify hazards, both in the interfaces and faults and in the integrated system design. And we've got to recommend necessary actions. So very familiar, very similar to what we've just heard. The difference here, of course, is we've got to look for hazards in the integrated system design. So subsystems on their own might have some hazards, put them all together, and we get emergent behavior, okay, from putting them all together. And safety is an emergent property, as we say, because, you know, a fault way down in a subsystem in a component might be of no significance whatsoever, but as it propagates up through the system hierarchy, it might become very significant. Okay, so let's take a particularly famous example. When the O-rings on the space shuttle solid rocket boosters failed. So the O-rings themselves were supposed to seal the segments of the booster. They got too cold, so they didn't work. They weren't flexible enough. So gas escaped from the solid rocket booster out the side. Okay, that could have been harmless, but unfortunately the hot gas was escaping in a direction that eventually melted a support strut and damaged the structure, which caused the solid rocket booster to push into the external fuel tank, and then the whole lot blew up. Okay, so what started as a relatively small, you know, underperformance by a synthetic rubber sealing ring, albeit a very big one, turned into the entire loss of the vehicle and all the crew. So that's how a relatively minor fault or failure mode or fault can propagate up through the system and cause big, nasty results. And that's what we've got to think about. So, bit of advice about task 205. The numbering and some of the text in the standard implies that you do 205 after 204, kind of on the way up on the right hand side of the V. But actually, of course, what we need to do is we need to do some preparatory work early. So when we're thinking about our system before we've even developed the subsystem specifications, we really do need to do some 205. Okay, So we need to do some 205 top down as we go down the left-hand side of the V, and we do that early. And those of you who've heard me talk before will know that I always bang on about doing safety analysis as early as possible, early enough to make a difference. Okay, so we do first pass through 205 early in order to gain some insight into what's going on, to influence the design, and to focus on those inputs and outputs that we're really interested in. And then as we come back up the V, we will do 205 again. And that second pass is the compliance exercise and verifying and validating that we've got the interfaces and performance, etc., that we need, that we must have. Or if not, what are the implications of that? So we don't do these tasks just once in sequence. We might do them iteratively as we go around the systems engineering V model. Okay, the life cycle, sorry. So yeah, so it's not just a linear once through activity. We need to think about what we're trying to achieve with these tasks and when is the best time to do them, and do them again. So in my commentary on the full lessons on 204 and 205, I do look at the differences. Yes, they have slightly different purposes. The timing, are we doing them top down or bottom up? Answer, probably both. Are we looking at the internals? Yes. Well, if we can. If we've got a bought piece of kit or we've got a supplier who won't give us any information, we may in fact have to analyze the subsystem as a black box because we don't know anything about it. So all we can do is look at the external behavior and the interfaces. Okay. And which techniques we're going to use, I've mentioned a few, and those depend on what we're trying to achieve and the limitations on the data that we're allowed. Okay, so you can't really do a very satisfactory failure mode analysis, or if you haven't got access to a failure catalog, or you don't know what the internal failures could be. So in that case, you just got to concentrate on the interfaces. And as I've said just recently, somebody should do task 205 early. So it might be the client and end user, the purchaser, or they might pay a prime contractor to do that work early to the integrator who's going to deliver the whole thing. But somebody should do some of that work early, preferably, as I say, preferably the client or the customer should do some, so that they're an informed customer, so they're an intelligent customer. That doesn't often happen, though, I have to say. Almost always, I would say, task 204 gets delegated to whoever is supplying the subsystem, or maybe the prime does it if they're buying something off the shelf. But yeah, again, think about what you're trying to achieve. Therefore, who should do it and when. And as it says, the two tasks are complementary but not the same. And if you remember that, you'll be fine with 204 and 205. Okay, so talked about 204 and 205, and they really go together, and we need to think about them together. One that we don't always do is system of systems hazard analysis. And which is task 209. And let me just have a look. So actually, before we do that, you recall the picture of the, here we go. So we recall this picture. We've got our system, which maybe is already in service. And then maybe we need to think about, well, how's it going to work with these other systems that might already be in service? So all of these things might have gone through a safety process in their own right, but now we want them to work together. So what might emerge? And So the purpose of task 209, it says, again, we're going to perform and document this system of systems analysis. It says to identify unique system of systems hazards. I'm not entirely sure that they're unique, or it is just about the hazards, as we'll see. But nevertheless, we're going to consider things at that level. And we will probably discover emergent behavior or performance issues or mismatch issues or harmonization issues, which lead us to generate special requirements to deal with these hazards and other challenges, which, as I say, wouldn't exist were these systems not interacting with each other. Okay, so we're really working at a high level on emergent behavior. Now, I'm going to talk about this using an example, because I did a big system of systems job way back in 2006, I think it was, when I'd just left the Air Force and joined a consultancy firm, and I got asked to do a job of this kind. In fact, we're just talking about a slightly disguised system here, or systems. So the challenge was we needed to assure the safety of a system for guiding aircraft onto ships, onto aircraft carriers in bad weather. Okay, and so we had to consider the ship and the special guidance equipment and the aircraft with the the pilot in the aircraft and the human operators of the sensors. Okay, and we had to take into account, as it says, human factors, the operating environment, which is very significant at sea, the operating procedures, and maintenance and management of the whole thing, which is complex. And yeah, so here we've got a little illustration. We've got our ship. We've got a radar and some other sensors mounted on the ship, and the radar is operated by an operator. That's actually an icon for a disc jockey, but nevertheless, it looks enough like a scopy to work. And then we've got our aircrew flying our aircraft who want to get back to the ship and land on it safely in bad weather. And of course, the ship is moving about on the sea. So it's all very challenging stuff. And what I've got here, this is a goal structuring notation representation of how we fixed, or we addressed the problem. And at the top, we wanted to be able to say that the entire, or the system is adequately safe for aircraft to locate and approach the ship and ultimately land. But the pilot does that, so we didn't have to worry about the final bit. And the approach we took to looking at all these different systems was to say, okay, we're going to look at all the three major elements, the three systems, and we're going to look at the way they interact. So, and we broke that down saying, okay, is each system safe to operate? Is the overall system of systems safe in operation? Have we met all the safety requirements, which were various? And are all the interactions between the three entities, are they all safe? So there was quite a lot of different things to do there. And that was all done. So that was the strategy in the dark blue. And then in the GSN, you can put the context around it. So you have all the information you need, but all the major argument, safety argument, is down the middle, and all the context and the is around the sides. So it works quite well. It simplifies the argument while providing all of the information that you need. Okay, we've defined what we're talking about. And then underneath those goals at the bottom of the page, we did the work to demonstrate it. But the point was, we have to start with each equipment or each system, because that's already a thing in its own right. It's been developed maybe to different standards than to what we're using. There's different definitions of risk, etc., etc., and that all has to be considered. So it's not all about hazards. Okay, the Mil standard can be a bit overly focused on hazards, and yes, they are important, hazards and requirements. That's good, but there is other stuff to consider as well, and making sure that all of these things are talking the safety language we're using. If it's either if it's not the same, is it compatible, and can we translate from one to another and achieve a satisfactory understanding of the whole system? Okay, because if we haven't done that, we're not necessarily going to spot the emergent properties. And I'm just looking at my watch because this is quite a long session and I want to leave time for more stuff. So the first thing to say, thank you for listening. We've gone through a few slides quite fast. I appreciate. So what I'm going to show you here, we've got some more resources that will help you. And as I say, all of these links are already in the chat. So there's a couple of free lessons, system safety concepts and principles, and what is system safety. So those are videos that you can watch from the website or on YouTube. I think system safety process is a paid lesson, so that's $45 US. And I've already mentioned the chat with me and Peter Bender about human factors. Again, that's free. And then finally, the final link is the free email subscription. So if you're interested in getting updates from me and discounts and freebies, click on that. No purchase is necessary. You'll get regular emails from me with what's going on, and you'll also get some hefty discount offers on my courses. So just a little plug there. So do go and check that out, please. As I say, there's no obligation to purchase anything. Or you can go to the website safetyartisan.com, and again you'll get the option there to subscribe for updates, freebies and discounts. But safetyartisan.com is where I live online. I'm also on Udemy, as I said, but that's the main site. And so this is the final webinar in this series. But what's coming next is I'm turning these webinars and these looking at the individual Mil standard tasks, and I'm going to bring those out as a set of mini courses on a full learning management system. Okay, so you can sign up for the courses, and they'll be structured as it says here. So we'll have, hazard identification, foundations of safety assessment, dealing with functional hazards, workplace hazards, and then this session. So I'll be pulling together quite a lot of material that I've developed over the years and putting it on the full learning management system, and there'll be a community as well. So there'll be community support and interaction and email support, and it features videos in much shorter chunks because that's how we tend to absorb information these days. So you can watch all of these things on your mobile device, and each session only lasts no more than 10 minutes. So you can work your way through the course as and when suits you. And there will be quizzes and assessments, as I say, and support from myself, and a monthly Q&A session with the community. So which is all part of the purchase price. So that is coming, and I'm aiming for the first one on 5 ways to identify hazards. I'm aiming to bring that out on the 1st of September. I'm going to write it down because now I've told you I've made a commitment. I better deliver. So that's enough from me. We're going to turn now to have a Q&A session. And you're welcome to ask any questions about the presentation, but also anything else about system safety. So let me just return. Okay. So thank you very much for listening. So does anybody have any questions? So we've got people have signed up with Eventbrite, and we've got people watching on YouTube, Facebook, LinkedIn, and I can't remember the other one. Yeah, anyway. Oh, Twitter as well, sorry. Not showing the usual symbol. So if you've got a question, do please type it in, and I will do my very best to answer you. And if I can't give you an answer straight away, I will go and research it and get back to you. And I will put the... Zoe has a question. Please go ahead. Okay, right, no worries. We're on the phone. Let's just... Okay, don't worry about the typo, Zoe. By the way, while Zoe's typing, the rest of you, anything you want to ask, do think about it and start typing. We will get round to everyone. So hopefully what we've done so far has given you an overview of how those three tasks work. And as I said, here we go. When we look at systems, subsystems, or system of systems, how do you define each? Arguably, each is a system at a different level. Yes, yeah, I would agree with that. It all depends on perspective. If you're looking on from the outside, your system of systems, it just looks like a system probably. Here's a system of systems defined as that because it is less tightly coupled. Right, okay. Right, and you're not familiar with the standards. Well, I'm not actually quoting the standards on how these things are defined. I'm trying to be more pragmatic. There are definitions in the Mil standard. So what I would say, yes, coupling is part of it, but practically speaking, I think what we're talking about is, I would say a system is something that exists and is working. It's in service. So it's a working entity in its own right. Okay. So the difference is subsystems on their own might be completely useless. You might have a control system, subsystem, but it's not controlling anything. So what? Or you might have components or, equipments that have no control. Again, so they're useless. Put them all together and you've got a working system, a working whole. So I would describe system of systems work as you've got a number of these independent systems that already work on their own, and now we've got to get them to work together. So that is how I would define it, which is not terribly scientific or precise, but I think it is practical, and that's what I've observed in my career, is that people have these things that exist, they're bringing something else in, and they want the whole thing to play nicely together, and that's where you have to do your system of systems work. So I hope that is a satisfactory answer for you, Zoe, and everybody else listening. Have we got any more questions? So if you're wondering whether to ask, do ask. There is no such thing as a foolish question. And, Benjamin, what's the major difference between task 205 and 204? It's one of perspective, Benjamin. I mean, they both ask you to do much the same thing. The only difference is it's just at the level. So the other thing worth saying is you're always going to have a system. Otherwise, there's no point in doing the safety work. So we're almost always going to need task 205 in one form or the other. Even if we've just bought an off-the-shelf system and it's a black box and we know very little about it, we've still got to learn about it. We've still got to read the user manual, etc., and try and work out what the hazards might be. Or maybe we do a physical inspection or a demonstration or a test, or a combination thereof to understand the hazards and requirements. But we're always going to be doing some sort of task 205 work. We might not be doing task 204. We might not have distinctive subsystems. We might have, as I say, a single black box entity when we've got no idea what the internal workings are. Or we might just have, we've developed a system and we've just put it together from existing commercial components, which we just bought, okay, which is getting more and more common these days, okay, with lots of different systems, particularly, in electronics and software and IT and so on, and communications and so on. You can buy a lot of stuff off the shelf with software definitions of how it all works. You put it together on a server rack and plug it in, stick it, maybe it comes with a user interface, or you buy one that's compatible and off you go. So then there may not be any subsystems as such. There might be no specified subsystem. Okay, so that, I would say, is the difference. Okay, so any more questions? Do please ask, because it's actually the most enjoyable part, I think, of the webinar, when we interact with each other and learn from each other. And in fact, that's going to be a big part of the online learning community when we get started in September. And by the way, the reason I've chosen the 1st of September is that is the 4th anniversary of my business. So I started this on the 1st of September 2019, and little did I know that we'd all be sat at home looking at our computer screens for the next 2 years. In fact, some of us still are. I'm working from home today. Yes, it was, I wouldn't say it was fortuitous, because I certainly didn't enjoy working from home all the time. But anyway, it gave me something to focus on, so that's a good thing. Okay, any more questions? All right. Okay, so, well, I think we'll end it there. Just remains for me to say thank you very much for watching. Thank you very much, everyone, for asking the questions. If you have a question that you didn't want to ask in front of other people, send me an email, go on, do a form submission on the website, send me a message on Facebook or LinkedIn or whatever, and I will answer your question. I might share the answer with other people, but I won't say who asked it. So if you want to ask a question in private, then do feel free to get in touch, or go and look at the materials on the Safety Artisan and see if you can get an answer there. But stay in touch, and I will. Oh, we've got another question. That's terrific. Thank you, Benjamin. Is the MIL standard different from CSM in terms of management of risk? Right, now, sorry, Benjamin. What is CSM? Apologies, I'm not familiar with the acronym. So while Benjamin's typing that out, as I say, I will also, for those who couldn't dial in or had to leave early, common safety method. All right, okay. I have to tell you, I have to admit, Benjamin, I am not familiar with the common safety method, but I will look it up. In fact, I'll do what doctors do, and I'll Google it in front of you while diagnosing your problem, which I've never been a fan of that. Why does the doctor? Common safety method. the common safety methods. All right. Okay. So this is a European Union thing? Is this a regulatory thing? Ah, right, for railways. Okay. Right. Okay, so we've got some EU directives for railway safety. Okay. Well, I'm not familiar. I'll go and look it up for you, and and in the UK as well. I'll go and have a look at those and let you know an answer. What I would say is that railways, generally speaking, use Senelec standards, which are the 5012 578 series, which are themselves, so they are functional safety standards. They're based on IEC 61508. So 61508 and that family of standards use very similar methods in terms of definitions. Oh, thank you. Start with CSMREA. Thank you. So the functional safety standards, they use a risk matrix, which is not that dissimilar from the Mil-Std. They use similar techniques and definitions, but the difference in focus is really the functional safety standards are interested in machines and systems that run typically for a long time, whereas a military system tends to have a fairly short and finite mission time. Okay, and that causes big differences in the way you approach safety. So functional safety is much more interested in long-term reliability, let's say. So there's a lot of stuff in the functional safety standards on how to deal with that. Whether that translates into your CSM measurements. Thank you, Zoe. Yeah, there are a few. I could see 6 on the website I was looking at. Yeah, without looking at them in detail, I can't give you an answer. But they probably use, given that the industry uses functional safety standards, they're probably not at a practical level. They're probably not that different. But I don't know what the CSM is looking for. But thank you. That is a new one on me, so thank you very much for that, Benjamin. Okay, have we got any more questions? Because I'm going to have to knock it on the head now. If you've got any more questions, do please send them in and I will share them. I will share the anonymized question and the answers on the social media platforms that we're on. Okay, well, thank you very much, everyone, for taking part. It's always a pleasure to interact with people who are interested in safety. And I'll be doing this at 5:30 p.m. local time today again. So you get another go at me if you choose to join me. All right. Take care, everyone. Bye-bye.